All right, guys, so we're going to talk about properties of integrals today. I'm going to share with you guys 5 properties of integrals and then how we can use geometry and these properties to evaluate integral expressions. So basically, just to kind of keep it short and sweet and to the point, a little more understandable, we're going to talk about 5 properties and how to apply them. Okay. Now, the first thing I want to do is I want to connect what we've been doing for the past 2 lessons to the rest of Unit 6. We're not going to be doing anything with the rectangles anymore, other than just for the sake of review. But those rectangles have something to do with integrals, right? We've been kind of talking about that already. So let's see what that is. All right, so consider this function here, f of x. And I want to find the area under the curve from 0 to 2. So 2 stops here, 0 stops here, and the area under the curve, what I mean by that is really the area between the function f of x and the actual function itself. I'm sorry, the x-axis. And so we have this. That's the area under the curve, so to speak. And the area under the curve is found with integrals, as we've learned earlier this year. This area is not very much, and the reason for that is because we have some positive areas here and some negatives, and so they cancel each other out. But that's the actual area under the curve. Okay, but what we've been doing for the past 2 days is we have been estimating area under the curve with rectangles. So let's say I wanted to break this interval up into, like, let's say 6 rectangles. All right, so this is a left-hand Riemann sum. I'm using left-handed rectangles, and 6 of them. And as you can see, the estimated area is about 2. The actual area is about 0.4. That's not a very good estimation. Now, how can I get a better estimation? Well, you could try a right Riemann sum. You could try a midpoint Riemann sum. Let's try doing a midpoint Riemann sum. We know that midpoint Riemann sums give us a better estimation. So here's a midpoint Riemann sum. So I've made my rectangles have midpoints. And as you can see, that's a much better estimate, a lot closer. And we learned that midpoint Riemann sums give us better estimations, right? But you know what? If we want to get better, an even better estimation, what we can do is we can increase the number of rectangles. So, like, let's say I wanted to increase this to, like, maybe 20 rectangles. That's a lot to break it up into, but check it out. Now, these are all midpoint rectangles, but as you can see, it's almost a perfect fit. I mean, there's a little, you could see each rectangle hangs over the line a little bit, over here especially, but overall, that's a pretty darn good fit. And look at the estimation. It's really close to the actual area under the curve. And so the point I'm trying to illustrate for you guys here is the fact that if we increase the number of rectangles, the more rectangles we make, the better the area looks. I can still see a little bit peeking over the edges here. Let's go up to 1,000 rectangles. Will it do it? I don't know if it'll do that many. There we go. Well, that's pretty much perfect at that point. And look at this estimation. It's almost exactly right up to the, whatever that is, like the millionth decimal place or something. So that's a really good estimation. So the more rectangles you have, even if I made this a left-handed Riemann sum, let's say, even if I did that, it still comes out to be darn good. So the point is that the more rectangles you have, the better. Okay? In mathematics, we use a symbol to represent adding a bunch of things together. It looks like this. Now, you don't need to write this down because we're not going to go over this very much. I just wanted to share the idea with you. But basically, if we take the base and multiply it by the height of every rectangle, and then we add all those together, from the first rectangle up to the last rectangle, that will give us an estimated area under the curve. Okay? But if I take the limit of this as n approaches infinity, in other words, the number of rectangles becomes infinite, this is no longer an estimation, but it becomes an exact area. So if you were to break this up into an infinite number of rectangles, you let those rectangles become infinitely small, and therefore you can fit an infinite number of them in there, then that's going to give you the exact area. And once you get that, the symbol we use for that is the integral, the definite integral, where a and b represent the left endpoint of 0, and 2 represents the right endpoint of 2. So b and a would be 0 and 2, so to speak. But there it is. So now in calculus, there are lessons we could do on this, and sometimes I throw it on at the end of the year about using this process here of adding together rectangles and finding its limit. I'm not going to get into that. I'm just going to tell you, though, for now, that the concept of putting rectangles under a curve and letting there become an infinite number of them is what leads to this. Okay? And so we've talked about estimating the area using rectangles. I've told you that if you increase the number of rectangles to infinity, you end up with an exact area under the curve. And then I've reminded you that that is the integral. So if your left-hand point is A, your right-hand point is B, if you want to find the actual area under the curve, in other words, what would the estimated area be if you let the number of rectangles be infinity? You would get the exact answer, and what would it be? It would be this integral value, which we've seen earlier this year. And we remember how to do that, hopefully. To find the value of a definite integral, you integrate f of x. Little f then becomes big F, also known as the antiderivative. And then you plug in the upper limit and the lower limit, and you subtract them. And that will give you the actual area under the curve. All right? Now we'll kind of be reviewing that a little bit as time goes on, but for the time being, that's enough to remember that. So let's go ahead and look at our properties. As I told you, today's lesson is going to be about looking at properties of integrals. And so here's our first property. Now I'm going to approach a lot of these properties in two ways: algebraically and then geometrically. Now all you really need to know is you need to understand what the properties are, but what I'm going to be writing over here on the right side, algebraically and geometrically, is I'm going to be doing that to explain why these properties are true. So why is it that the integral of f of x from a to a equals 0? Well, what you do first is you integrate little f and you get big F, right? And then we're going to take big F and we're going to plug each of those a's in and subtract it. Well, if you subtract something from itself, then obviously it's 0. So that makes sense. That's the fundamental theorem of calculus there. All right, but let's think about that geometrically, okay? So we're talking about a curve here, a function f of x. And when we're doing the fundamental theorem of calculus, we usually start at a number and then we end at a number. But if I asked you what's the area under the curve from A to A, what's the area of this line? There is no area because we don't have a rectangle. No rectangle equals no area. Now if I were to go from A to B, well, now you've got a rectangle, right, that you could estimate. But if you're just stopping at one single point, of course you can't have an area under the curve. So that's the geometric explanation of this property 1 and the algebraic explanation of this property 1. All right? So anytime the upper limit and the lower limit are the same, the outcome will be 0. That's property 1. Let's go ahead and continue. So here's property 2. Well, let's evaluate this algebraically first. In other words, using the FTC, the fundamental theorem of calculus. So let's do this first. So if I integrate little f, it becomes big F. I plug in the top one, and then I plug in the bottom one, and I subtract those, right? Let's do that on this side over here. Same thing, integrate little f, and you get big F. Plug in the top one, and subtract from that the bottom one. But there's a negative in the front. I'm telling you these things are equal. And that's true. Because on the left side, f of b is positive and f of a is negative. On the right side, though, they're opposite. F of a is positive and f of b is negative. So if we put a negative in the front and distribute it in, that will make them become equal. And so this property basically tells us that if you have a definite integral, you can flip these two numbers around, which we're going to have to do today at some point. You could flip the b and the a around, and that's totally allowed, so long as you put a negative in the front, because that makes them become equal. So basically, those two areas are exactly opposites in signs, is what that is saying. Now, geometrically, what does that mean? If you're starting from A and you're going towards B, your area will be normal. So for instance, if I were integrating from A to B, I would have a positive area here. But the reason I would have a positive area is because it's above the x-axis, by the way. But let's take this same graph and the same interval from A to B. But let's say that I was integrating backwards. Opposite signs result. So whenever you integrate from left to right, you get a normal area. And what I mean by normal area is above the curve is positive, below the curve is negative. Let's write that. But when you integrate backwards from right to left, you get opposite signs. In other words, if it's above the curve, if it's above the x-axis, then you end up with a negative area. And if it's below the x-axis, then you'll end up with a positive area. So it reverses the signs. So there's two ways to think about it. Algebraically, we can prove it there using the fundamental theorem of calculus that yes, you get the same answer, just opposite signs. So we just put a negative in the front and they become equal. Geometrically, you can think of it as integrating from left to right, positive area above, negative area below. But integrating right to left flips it. Above the x-axis means the area is negative, below the x-axis is positive now. Okay? And how are we going to be using this property today? Basically, we're going to be forced to flip these around, and when we do that, we're going to want to put a negative in the front. So that's property 2. All right, property 3, I'm not going to spend much explanation on. This is a property that we've already seen. But anytime you have a constant multiplier, you can just pull it out to the front. Okay? We've been doing that with integrals since our second unit. And we've also been doing property 4 since we first started our second unit. Where if you have two functions that are being added and subtracted together and you wanted to integrate this, you could just integrate each piece separately and then add them together. So basically what this means is you can add the functions together and then integrate, or you can integrate each function separately and then add. But either way, you get the same answer. And typically, we're going to want to break them up. So it'll start off as them being put together like this, but we're going to want to split them up. All right. So let's take a look at property 5. Now this one's a little bit strange, but check this out here. I'm going to make this kind of long. I'm going to say we start here at A, right? And we're going to end at C. And then here's my function. We'll just say it looks like this. So the area under the curve from A to C is represented by this integral. Now, the area under the curve from C to B. So now I want to go from C to B. So I'm going to pick up where this one left off, and then we're going to stop at B. So my function is going to keep going like that now. This first area stopped at C, but now this next area is going from C to B. So the area under the curve from C to B is this. So the area under the curve represented by the red region is this first integral here on the left. And the second area represented by the green region is this integral here on the right. Well, can't we just put those two areas together and go all the way from A to B and get a total area? Yes, we can. And so that's basically what it's saying there. It's saying if you have an area, one half of an area and another half of an area, and you put those two areas together, you get one big area, basically. But the point is that these things are connected. Where this one leaves off, this one stops at C, that's where this one picks up at. That way those two areas are actually connected together. Okay, so long as you have one area connected to another, you could take those two little areas and add them together into one bigger area. Now, how we're going to be using that today then is you're going to be noticing that, oh, where this one leaves off, this one picks up. And so we're going to put the function to get those two functions together as one, where we start off at A and end at B and eliminate the middleman. We don't use that anymore. So you take your first starting point, you connect it with your last ending point, and just put it together as one integral. So that's going to be the idea there. All right. The last property we're going to look at is this one. This one's kind of interesting. We'll look at this one once again algebraically and geometrically. So what I want you to understand here is that this is a constant function. Okay, it's a constant function. It's just a number. Now, when you integrate a constant, basically you just put an x next to it. So if we integrate c, we get cx. And we're going from a to b, right? So then we plug in the b, and we plug in the a, and we subtract them. Now notice both of these terms have a c. I'm going to go ahead and factor that out, and I get this. So there's your algebraic explanation for why this thing has that answer. A little bit complicated and not too friendly to look at, but there it is. Now the geometric one I find to be particularly interesting and a lot more helpful in finding out the answer. I'm integrating a constant function. Now what does a constant function look like? A constant function looks like a straight line, doesn't it? A constant function looks like a straight line. So if I'm going from A to B, and I want to know what is the area under that curve from A to B, well, it's just a rectangle, isn't it? What's the base of this rectangle? How long is the base of my rectangle? Well, the base of my rectangle is B minus A. What's the height of my rectangle? Well, it happens to be the function c. And as you guys know, the area of a rectangle is height times base. And the area under the curve is represented by an integral. So since we have a horizontal, a constant function, it's literally, the integral is not estimated by a rectangle. The integral actually literally is a rectangle because it's a flat line. And because of that, all you need is the function's height, which is c, multiplied by its base, which is a, b minus a. So in other words, if I were to give you guys something like this, 2 and 5 and 6, you could do this the hard way, and you could integrate that and get 6x. And then you could do 6 times 5 minus 6 times 2. And you would get 30 minus 12, which is 18. That'll work. But there's a much faster way. If you just remember that this is a rectangle because this is a horizontal line, my height times base will be, the height is 6, the function itself, and the base is the distance from your first endpoint to your last. So 6 times 3 is 18. So much faster if you think of it geometrically. Okay, but there it is. When you have just a constant function here, you might want to draw an arrow there and put constant. That's how you can calculate the area. Very quick. Very quick. All right, and so there's our 6 property. I said 5, but I forgot I added that 6th one in there. We're going to go ahead and start putting these things to use for us here. All right, so up at the top, I've given us some information. I've given us the value of various integrals. So the integral from 0 to 6 is 72. So I'm sorry, I have to say that again. So the integral from 0 to 6 of the function x squared is going to be 72. The integral of the function x from 0 to 6, I'm going to tell you, is 18. And the integral of this mystery function here, f of x, from 0 to 3 is 10. And the integral from 3 to 6 of this mystery function is negative 8. I'm calling this a mystery function because we don't know what it is. I'm just telling you we have some function called f of x. Over here, we could actually calculate these ourselves and prove that this is, in fact, 72. But we're not going to. I'm just going to tell you that's what the answer is. So our goal here is we're going to evaluate each expression below using the properties that we've just learned and these values that they've given us. So here we go. Number 1. Now, we could do this the old school way. It'll totally work because I'm actually giving you something you can actually integrate. And you'll get the right answer. But I don't want to go that route today. I want to use the properties instead. Okay? So the first property I want to use here is property 4. So take a look at property 4. Take a look at property 4. According to property 4, if you have two functions that are being added together, you could split them up, right? I would encourage you guys, you don't have to do this on a test, but for your notes and your practice problems today, I would encourage you to label what properties you use. It'll help you a lot whenever you're studying for your test and quizzes to know what properties you applied to get from one point to another. So according to property 4, I could split these two integrals up into two separate integrals. Okay? Now, we already know what this equals. Up here from above, we see that the integral of x squared from 0 to 6 is 72. We also know that we have another property here actually. I have a constant in front of my x. I know that I'm allowed to take that constant out. Why am I allowed to do that? What property is that says if you have a constant you can just take it out? Let me back up. I got to find it here. Sorry, you guys probably can't see it very well because I've got writing on the screen. There it is. It's property 3. So go ahead and take a look at property 3. According to property 3, anytime you have a constant multiplier here in the front, you can take it out of the integral and put it up front there. Now that I've done that, I've got just this basic integral right here, which I know the value of. The value of that integral is 18. And now that I've done that, and let's label that, by the way, that's property 3. Now that I've done that, I can go ahead and calculate this. I can do 4 times 18, and then I can add that to 72, and I'll get my final answer of 144. So that's what I want us to do today, is I want us to apply the properties. So I use property 4 to split it, and then I use property 3 to take the constant multiplier out, and then we just replace each integral with what we already know it to equal up here and simplify it. Okay, let's take a look at another one, number 2. So for number 2, I've got an integral here. Now, all I have inside of that integral there is a constant. There's just a number there. That's my function is a straight line function. Which property is that? That was this property, where if you just have a number right here, that represents your height, and the base represents the difference between your upper limit and your lower limit. So if I wanted to calculate this one, according to property 6, you put your height here, which is 3, and your base is the top limit minus your lower limit, which is 18. So property 6 gets us an answer pretty quickly. Now, once again, just like number 1, we could integrate this the old way, you know, where you add 1 to the power and divide by that number, and then do the fundamental theorem of calculus, or you could even use a calculator. You'll get the same answers. But I'm just showing you, since I've already given you this information up here, we can use our properties to get the answers quicker. All right? All right, let's go ahead and take a look at number 3. Now, by the time we get to number 3, I'm hoping that you guys are starting to understand the process a little bit here. So I'm going to pause. I want you guys to pause the video, and I want you to think, what property do you think I'm going to do first here? So pause the video and think for a second. What property is Mr. Bailey going to do first on number 3? All right, well, as you can see, I've got multiple pieces being added together. So just like I did on number 1, the first thing I'm going to apply is property 4. Property 4 is the one where you split it up into separate integrals. So I'm going to take the integral of 2x squared separately from the integral of 5x and the integral of 4. So that's the first thing I'm going to do, split each of those pieces up. Okay? All right, now what would I do? I've applied property 4, but do these integrals look anything like the ones that we have? Not yet. Something's wrong, right? So what property am I going to use so that I can get these integrals to look like the ones up there, so I can just plug in the answers that I already know? What property am I going to use? Well, hopefully you guys noticed that, oh, there's constant multipliers here. So because of property 3, I could take those numbers out of the integral like this. And by doing that, now my integral pieces look a lot more like the ones that are up top there. Now you're going to notice I didn't do that with this last one, because this last one is different. But I did it with the first 2. With the first 2, we had a constant multiplier, so we could just take it out like that. Okay? So now what? Well, just by substitution, we can do this. So the integral of x squared from 0 to 6, that equals 72. The integral of x from 0 to 6, we already know that also. That's 18. But this last one here is a little bit different. Stop the video if you need to and think about, what property can I apply to this one? Hopefully you guys saw that, oh, that's property 6 again, just like number 2. I've got a constant function here. So understand, there's a difference between a constant multiplier, A constant multiplier is where you have a number multiplying something that's already there. And for those, we just take it out. But if you have just a constant that's not multiplying a function, it's just the constant all by itself, we're going to apply property 6. And according to property 6, it works like this. You take your height, which is 4, and you multiply it by your base, which is the top minus the bottom. And then from there, we're ready to start calculating our answer. So 2 times 72 is 144. 5 times 18 is 90. And then 4 times 6 is going to be 24. And then when we put all that together, we'll have our final answer. And I end up with 210. So the first thing I did was I applied property 4 to split up each piece. Then I applied property 3 to take the constants out of the integrals. So that way they look exactly like the ones that I have here, and I can just substitute. But we also had the constant function here, which we applied property 6 to. Right? So there's that. Now, you might think, well, Mr. Bailey, thank you for that. That was a new piece of information, and quite frankly, I would have been fine without it because I can do this the old school way anyway, and less information is good because my brain is kind of tired of shoving new stuff in. Well, okay, that's fine. But the problem is that you wouldn't be able to do the rest of this worksheet without knowing the properties. Because for numbers 4 through 6, I don't tell you what the function is. I just tell you that there is a function there, and we're going to call it f of x. So for these ones, you would have to actually know the properties in order to pull it off. Okay? So the goal is I want to make this look as much like one of these as possible so I can get the answer that they give me. So I want to end up with f of x from 0 to 3, or I want to end up with f of x from 3 to 6 so that I can get these numbers here. Okay? So right now, there's a couple of problems with this one. First of all, you'll notice that there's a 6 in the way. I don't want that there. But luckily, what property allows me to take that out? Isn't that property 3? According to property 3, I could take a constant multiplier out. But we're still not quite okay. Because this integral doesn't look exactly like this integral yet. Do you guys see what the problem with it is? They're a little bit different. What is it? They're opposites. This one has a 0 on the bottom and a 3 on the top. This one's got the 3 on the bottom and a 0 on the top. So we need to fix that situation. Now, what property was that where the limits are flipped? It was this guy here. So A, B, BA are equal if there's an opposite sign. So let me show you how we're going to use that here. So I want this thing to look like this thing. So what I'm going to do is I'm going to flip those limits around, which I'm totally allowed to do so long as I put a negative in the front. And that was property 2. So I'm allowed to flip those limits around so long as I put a negative in the front. Now I've got this looking exactly like this. And now that they look exactly the same, I can replace it with what it equals, 10. So I can replace that with 10, and I end up with negative 60 as a result. So I applied property 3 to take the constant out, and then I applied property 2 to flip the limits around, and then we calculated the area from there. All right, let's do another one. I want to figure out what is the integral of f of x from 0 to 6? Well, I don't really have an integral up here where f of x goes from 0 to 6. I've got one that goes from 0 to 3. I've got one that goes from 3 to 6. But I don't have one that goes from 0 to 6. This one might be one of the trickier ones, I'm not sure, but it's actually this property right here. Let me back it up a little bit. Or maybe you can think about it for a minute. What property do you think it is? It's this one. The integral from a to b is the same thing as taking the integral from a to c and adding that to the integral from c to b. In other words, if I find the area from 0 to 3 and the area from 3 to 6, and I put those two areas together, that's just going to tell me the entire area from 0 to 6. Okay, so according to property, what was that? I've already forgotten. I think it was property. I forgot. I got to go look again. Property number 5. Okay. According to property 5, the area from 0 to 6 is the same thing as finding the area from 0 to 3 and adding that to the area from 3 to 6, just splitting it up into two separate integrals. Okay? Now, the area from 0 to 3 we know is 10, and the area from 3 to 6 we know is -8. So the final answer would be 2. So that's property 5. That's property 5. All right, how about this last one here? I want to find the area under the curve of f of x from 2 to 2. Well, take a look. What property is that? That's property 1. Anytime the bottom limit equals the top limit, you don't even have a rectangle. It's just a straight line. There is no area, so the answer is 0. That's property 1. Now I just want you guys to know the numbers, the way that I've chosen to name these properties is completely arbitrary. I call it doesn't matter which the name. I made the names up, in other words. So you can't say property 1 on your AP test. So don't memorize the names. Memorize the properties. Okay. The only reason I'm using names is so that you have a reference to go back and see what property we used. You do want to know the properties, but we don't name the properties of those things. We're just doing that in our notes to help ourselves. All right, so here's some student practice here. When you unpause the video, I will go through one problem at a time with you here. So go ahead and pause the video here and do number 1. And when you unpause the video, you will see the solution for number 1. So for number 1, I applied property 3 first, and I took the half out because that's a constant multiplier. After I took out the half, this integral matched this integral, so I can just replace that integral with what it equals, 60. And so half of 60 is 30. So that's the answer number 1. Go ahead and pause the video here and do number 2. See what property you would apply to it. All right. I applied property 6. Since it's just a constant number there is 7, property 6 says we could do 7 multiplied by the difference of the limits, 5 and 2. 5 minus 2 is 3, and 7 times 3 is 21. Pause the video here and try number 3. All right, so step 1 is to apply property 4 and to split the integral up into 3 separate integrals. Next, I can replace this integral here with 60. The next one, I can take the -3 out using property 3. Now that I've got this integral, I know that that equals 6, so I can replace it with 6. And for this one here, I apply property 6 to it because it's just a constant function. And then doing my math there, we end up. All right, now for number 4, a little bit tricky. So the first thing I'm going to give you a hint. The first thing I would like you guys to do is I would like you to apply property 2. So start with property 2. After that, see if you guys can figure the rest out. Okay, when you unpause it, I'll show you the solution. All right, so here's the answer. Property 2 is where we're going to flip the -2 and the 4 around, and we're going to put a negative in the front first. After that, I'm going to apply property 5 because we don't have an integral up here with f of x in it that goes from -2 to 4. I've got one that goes from -2 to 0 and then from 0 to 4. So I know that if I put these two together, that would give me the whole thing. So this integral can be split up into these 2 separate integrals being added together, and that's property 5. Notice I keep that negative there on the outside as I do that. Then I substitute the given values in and simplify to get -20 as the final answer. All right, let's go ahead and pause the video here and see if you guys can get the answer to number 5. Now you guys might have did a lot of properties, like maybe you did property, I want to say 4, I think, is the one where you've split it up into 3 separate integrals. Maybe you did property 3 and took out the constant multiple here. But honestly, you didn't really need to do any of that because all of these integrals are going from 5 to 5. And so every one of these things is going to turn out just to be 0 anyway. So that's property 1. Anytime your integral has the same number on top and bottom, the whole thing is going to come out to be 0. So you might have went through all the work of applying a bunch of different properties, but either way, you would have ended up with 0 at the very end anyway. Or you could have just caught that at the beginning and noticed the whole thing is 0. All right, so now we're going to switch gears a little bit here. Let's move on to number 6 and see if you guys can do that one. So go ahead and pause the video. When you unpause it, you will see the solution. All right, so final answer on that one's 50. I think I wrote it wrong. Let me bring it back here really quick. It's 56, not 50. 56 is the final answer. So property 4, first of all, I'd write each piece of these in their own integral, which will give me that. Next, this guy here, we can apply property 3 to it and get this as a result by taking out the constant. This guy here equals 60. So we can just replace that with 60. This guy here, we don't have an integral that goes from -2 to 4 with the f of x in it, but we do have these two pieces that when you put them together is the same thing using property 5. And then we go ahead and replace this piece with 6, this piece with 20, and this piece with 40. And then we just have to do all our math and combine those numbers together, and we end up with 56 as the final answer. So I use property 4, property 3, and property 5. Got our final answer. So those are properties of integrals there. I'm going to go ahead and take a look at some other types of questions or ways that this question can be asked. So let's move on to example 2 here. All right, so for this example, I want you guys to notice something interesting. We start off with some given stuff once again, and then they're going to ask us some questions. But I want you to notice something interesting about the given information here. My first one is going from -2 to 3. So you don't draw this because it's not an accurate picture. But if we start off here at -2 and we're going to go all the way up to 3. So that first portion, I don't know what the function looks like, but let's just say it looks like that. So we're going from -2 to 3. That's this integral, and apparently that area under the curve is 4. Okay, but the interval from 1 to 3 is 8. So from here to here is 8. So we have two pieces. I've got a left-handed piece here, and I've got a right-handed piece, and then of course we have the entire thing, right? Well, the entire thing, which I've highlighted in red, is this integral right here. We're going all the way from -2 to 3. But this one here matches the green area. Now some of you guys might notice, Mr. Bailey, why is the green area equal to 8, but the whole thing equals 4? Wouldn't the green area have to be smaller? The answer is yes, and that's because my picture's not drawn right. What that would mean is that somewhere along the way this area actually dips below the x-axis, so that yes, from 1 to 3 we have a +8 area, but somewhere to the left of that it should be below the x-axis, causing the total area to come out less. But I don't care about that right now. I don't want to stress on that. All I want you guys to notice is that there's 3 parts here. You have the orange part on the left, the green part on the right, and then the whole thing, which is in red. And so before we even begin, I'm going to start off with property 5, just to kind of get some more information out of this, because if we don't start here, it'll make things a little bit trickier as we try to do these problems that are coming up. So according to property 5, the entire area, which is the integral from -2 to 3, should be equal to the integral of -2 to 1, that's the orange area, added to the integral for the area of the green region, which is from 1 to 3. Okay? Now, I'm still going to do a little bit more here to help me make sense of this. The next thing I'm going to do is I'm going to plug some actual numbers in here. We know, for instance, that this, write that better, sorry about that. We know that this integral right here is equal to 4. So I'm going to put 4 right here equals, and then we're going to have our orange region. Now I don't know what that one is yet. I don't know what the integral from -2 to 1 is yet. They didn't give me that. But they did tell me the area of the green region. The green region from 1 to 3 is right here. It's 8. So, but here's the thing. Don't you guys see? We can very easily find out what that orange region is now. If blank plus 8 equals 4, then I can figure out what that blank is. Right? We can just do some basic math. So 4 is equal to blank plus 8. So let's just subtract 8 on both sides and we can get our blank. So that missing area now we know is -4. So I'm going to come up here and I'm going to replace that with -4. All right. Now that means I just discovered a new piece of given information. And I'm going to add it to my given information. All right. Having some technical issues here. Just a second. There we go. So I just discovered some missing information myself using property 5. So I'm going to put therefore the integral from -2 to 1 we just figured out has to be equal to -4. Okay, so I'm going to do that before I even begin the problem. Okay, the rest of it is going to be very straightforward, very much like what we've done already. So I don't want to spend too long on that part. So I'm actually gonna skip these for now, and I want you guys to do the same thing on the student practice I've got coming up. So let's review. What did I do here first? First of all, I took these two things and I applied property 5 to it to create an equation. Then I used that equation to find the missing piece. Once I had that missing piece, then we can go ahead and start answering the rest of these questions, all right? So why don't we pause here really quick and let you guys do this one here. So pause the video and see if you guys can calculate the missing piece. So if you haven't done it yet, you might want to pause the video because I'm about ready to start going over it at this time. Now, as you can see, if I'm going from 1 to 4 here, and this one's going from 1 to 2, then this must be a part of this one. So this one here is the big one here. So from 1 to 4 is the whole thing. And that must be equal to this one, from 1 to 2, being added to what? Well, I want to get from 1 to 4, right? Well, I left off at 2, so this one needs to pick up at 2 and stop at 4 then. And that's my missing piece. Now, according to the problem, the whole thing is equal to 10. So this side equals 10. The piece over here that they gave us is equal to 4. So I'm going to put a 4 here. And then the missing piece, the one that I don't know yet, goes here. And then if we go ahead and just subtract this 4 here on both sides, we will have our answer for what this missing piece equals. And that is this. So hopefully you guys were able to get to that. And now that we've gotten that missing piece, the rest of the problems below actually come out to be a little bit simpler. Okay, so at this point I would encourage you guys to go ahead and pause the video and see if you guys can answer questions 1 through 3 on your student practice using the 2 pieces that they gave us, as well as this 3rd piece that we found. And when you unpause it, I will have the solution available for you. So for number 1, that was our missing piece that we found. So we already did the work for number 1. That's 6. For number 2, it's the same thing. It's just that these limits are reversed. So this one is the same thing as this one, with a slight difference of being negative. And so this one's answer will actually be -6. And then for the last one here, we can apply property 4 to split these up. Here I can apply property 3 and take out the constant. Here I can apply property 6. Here I can substitute that with what I know 2 to 4 be, which is 6. So now we've got 4 times 6 plus 3 times 2, which is 24, plus 6, which is 30. And there's our final answer. So you will see some problems on your homework where, yes, they're going to give you some given information, but you're going to find that as you get started, you're like, what the heck? Where'd that come from? That's not up here. And what you have to do is you have to find that missing piece. So when you're doing your homework and you get to a place where you're kind of stuck because they're asking for a piece that you don't have, that means you need to apply property 5 to find that missing piece. And that'll do it for our lesson today. So until next time, we'll see you then.